The AI data landscape is loud right now. You hear terms like vectors, tensors, and arrays tossed around in every architectural meeting, often as if they all mean the exact same thing. And mathematically speaking, they are closely related. At its core, a vector is technically just a one-dimensional tensor. Because of that shared math, it is incredibly common for engineers to assume that a tensor database is simply a more advanced, premium version of a vector database. But in the actual data engineering ecosystem, that assumption will get you into trouble. These two terms describe entirely different architectural workloads. The choice between them comes down to a specific split in how you handle data. Are you building infrastructure designed for finding data, or infrastructure designed for feeding data? Provisioning the wrong database based on industry hype, instead of matching your specific workload, results in severe performance bottlenecks and a waste of expensive compute resources. Let's break down which one you actually need. Let's look at the finders first. Vector databases are built with a single, highly specialized primary data format, storing one-dimensional embedding vectors. A text document is mathematically converted into a one-dimensional array, a vector, and stored. When querying, the system calculates the mathematical distance between that query and stored vectors. By measuring distances, it retrieves nearest neighbors, finding points with the closest semantic meaning. Because of this hyperspecialization, a vector architecture is optimized for powering retrieval-augmented generation, or RAG, pipelines and semantic search tools. If this is your workload, you will be looking at platforms like Pinecone, Milvus, or Qdrant. They dominate this specific space, but their specialization is exactly what limits them. Vector databases process one-dimensional embeddings. They cannot natively handle the massive, unstructured, multi-dimensional raw data that custom AI models are actually trained on. For RAG builders trying to retrieve text to feed an existing large language model, vector databases are the exact right tool. But if you need to process raw media, they hit a wall. This brings us to the feeders. A 3D medical MRI scan illustrates the kind of complex, multi-dimensional data that tensor databases are built for. We are talking about massive, unstructured inputs like dense video files or petabyte-scale satellite imagery. This represents an n-dimensional data cube. A tensor database performs multi-axis slicing across dimensions at massive scale. It streams these operations directly into deep learning frameworks like PyTorch and TensorFlow, avoiding slow disk bottlenecks. The result is that your highly expensive GPUs stay constantly fed and utilized during heavy model training pipelines. There's no waiting around for data to load into memory. The notable systems built specifically for this heavy lifting include ActiveLoop Deep Lake, TileDB, and Google's TensorStore. However, implementing these systems introduces severe infrastructure complexity. You are adopting a steep learning curve and a total shift in how your team processes and stores data. Tensor databases are strictly for deep learning architects who are training their own custom models. If your team is just building text-based chat applications, deploying a tensor database is overkill. So what happens when an enterprise AI application requires both? You might have petabytes and raw video training data, but you also need structured metadata search and relational queries. The Duck Stack bridges raw deep learning and standard analytical workloads. On the left, a tensor store holds multidimensional data, streaming it to GPUs. On the right, an analytical engine like DuckDB handles metadata and one-dimensional vector searches. Together, this architecture acts as a comprehensive data lakehouse, giving an AI team the tooling to handle both large-scale training and precise semantic retrieval at the same time. The severe trade-off here is overhead. You are now responsible for managing, maintaining, and syncing two disparate database systems. While this hybrid approach gives you total flexibility, it demands a highly skilled data engineering team to maintain the integration and keep the data pipelines from failing. Making your choice comes down to one clear distinction. Vector databases are for finding, tensor databases are for feeding. This decision tree starts with one question before provisioning infrastructure. What is your primary AI goal? If you're retrieving info to contextualize an LLM, follow this path. Your destination is a vector database. For semantic search or chatbots, the nearest neighbor math of a vector database is exactly what you need. But if you are a deep learning architect working with petabyte-scale media, you take the second path to a tensor database. Custom model training on unstructured data requires multi-axis slicing and direct hardware streaming. Here, a tensor database is a mandatory investment. Never buy a database simply because the terminology sounds more advanced. Look at your workload, evaluate your inputs, and always buy the infrastructure that precisely matches the dimensionality of your data.